This video will solve problems 1, 2, and 3 from the 2016 AP Calculus AB exam. So we're going to do 2016 AB Calc free response numbers 1, 2, and 3. Now, it should be noted that free response questions 1 and 3 were also on the BC test. So, 1 and 3 also BC exam. All right? So if you're here looking for questions for the 2016 BC Calculus free response, questions 1 and 3 are going to be on this video. All right, so we'll start with question number 1. Now, question number 1 is similar to other questions we've encountered while looking at the calculus free response questions from the College Board. They give us derivatives that are not blatantly identified as derivatives. They're not obviously identified as derivatives. So we read the problem and it says water is pumped into a tank at a rate modeled by. So this is question number 1. Water is pumped into a tank at a rate. And as soon as we see those words, we know we're discussing a derivative, rate of change. That's the derivative. And they give us a formula for that. They tell us W of t equals 2,000 e to the negative t squared divided by 20. 2,000 e to the negative t squared divided by 20. That's liters per hour. That's the rate at which water is being pumped into a tank, right? Rate. So that's the derivative. That's the rate of change. That's not how much water is in the tank. That's the rate the water is going into the tank. Since this is a derivative, if we want the amount of water in the tank, we're going to have to integrate this. We're going to have to use the net change theorem, take the integral of the derivative. The integral of the derivative would make the derivative go away, and we would have the amount. So right now we have the rate, and they tell us this is valid between 0 and 8 hours. So we have water being pumped into a tank between 0 and 8 hours. The problem goes on to say water is removed from the tank at a rate modeled by, so this is in, we'll put in under this. Water is removed, right, at a rate. And then they give us R of t, and they tell us this is the water going out of the tank. Now, they don't specifically give us a function for the rate at which the water goes out of the tank. Sometimes in a problem like this, they give us a function for this and a function for this. Sometimes they don't give us a function for one of these, but instead they give us a table of values, and that's what they've done in this problem. They said water is removed from the tank at a rate modeled by R of t, liters per hour, so this is liters per hour, same units, where R is a differentiable and decreasing function. So, what do we know about R? We know R is differentiable and decreasing. Now, they don't give us information we don't need. So since they've told us R is differentiable and R is decreasing, then we know something about R. If it's differentiable, we immediately know R is continuous, right? Differentiability implies continuity. So we're going to write that down. We may not need it, we may need it, we don't know. We're going to put it down just in case we need it. And they tell us that this is true for 0 is less than or equal to t is less than or equal to 8. All right? Now, it also says at t equals 0, there's 50,000 liters of water in the tank. So at t equals 0, capacity is 50,000 liters. Okay? Excuse me. All right. A says, part A, says estimate r prime of 2. Now they told us r is differentiable, so we can find its derivative. So they want us to find r prime at 2. Now we can't take the derivative of r, we don't have the function. If we had the function, we would simply take its derivative using one of our derivative rules. We would plug in 2. If they wanted me to take the derivative of w, I have derivative rules that would allow me to do this. I could do this derivative with the chain rule. I'd plug in 2 and I'd get the answer. However, what they're trying to make sure we understand is there are ways to estimate the derivative, because the instructions literally say estimate r prime of 2. They don't say find r prime of 2. It says estimate r prime of 2. Show the work that leads to your answer. Indicate your units of measure. Whenever they ask you for units measured, please don't forget them. They're always worth a point. So how am I going to find r prime of 2? I'm going to use my secant line analysis, right? I'm going to estimate the derivative. I have my table up above. They asked me for r prime of 2, so I'm going to say r prime of 2 is approximately equal to the secant line that I can use to closely resemble r prime of 2, the one that most accurately resembles r prime of 2. Now I could go from 0 to 6 or 0 to 1. Those span 2. I could go from 8 to 0. I'm talking about the time here. Those all span 2. But they've given us 3 and 1, so that's the most reasonable. So we're going to find r of 3 minus r of 1 divided by 3 minus 1. Change in y over change in x. Now r of 3 is 950. Getting that from the table. R of 1 is 1190. And of course, 3 minus 1 is 2. And so if we do our arithmetic here, we get negative 120, which makes sense, right? Negative 120 liters per hour. But that's not our units, is it? Because our numerator is liters per hour. Our denominator is hours. So this is liters per hour squared, right? Liters per hour squared. It makes sense that it's negative, because let's think about our function here. R is differentiable and decreasing. So we know our function is decreasing. It says so right here. It says it's decreasing. This is the derivative of r, and so therefore the derivative of r is the slope of the tangent line, and therefore it's going to be negative. So this problem makes sense. Our solution makes sense. Now part B, right, part B says use a left-hand Riemann sum. Now that's a change. Normally in the AP test we're conditioned to use right-hand Riemann sums, but this year they want us to use a left-hand with the 4 subintervals indicated by the table. Now our table goes 0 to 1, 1 to 3, 3 to 6, 6 to 8. Notice those are not equal widths. 0 to 1, 1 unit wide. 1 to 3, 2 units wide. 3 to 6, 3 units wide. 6 to 8, back to 2 units wide. So they're asking us to find a Riemann sum using non-equal widths. It's not a big deal. We can still do it, but instead of having one delta x for the width, we're going to have to plug in a separate delta x. So it says use a left-hand Riemann sum with the 4 subintervals indicated to estimate the total amount of water removed from the tank during the 8 hours. So that's the first thing we want to do. We want to estimate the total amount of water removed from the tank. The amount of water, right? We want to estimate the amount. We know Riemann sums estimate integrals. So that's a clue. Plus, we've already discussed this is a rate. So if I want to get the amount, if I want to know the amount removed, I have to take the integral between 0 and 8. That's what's going to tell me the amount removed. Now, how am I going to find that? Well, I can't integrate r. They didn't specifically give me r, but in the problem it says use a left Riemann sum with 4 subintervals to estimate, right? Not to find, to estimate. So we're going to get an approximate answer here. Now, what does our chart look like? Well, if we were to, we have 0, right? We have 1, we said we have 3, then we have 6, and then we go to 8. That's what we said our values were for our times, right? So we'll stop this right here at 8. We said our function's decreasing. So we have 11, we have 1340 here. I'm just going to squeeze it in right here. So we have 1340, so we'll put that dot right here. And then at 1 hour, we're down to 1190, so we're lower, right? We're going to just put that dot right here. At 3 hours, we're down to 950, so we'll just put that right here. Now, this is not a line, it's a decreasing function. At 6 hours, we're at 740, right? 740, so we'll put that here. And then finally, at 8 hours, we're at 700, right? So our function is decreasing like this, which is what they told us was going to happen. Now, they asked us to use left-hand Riemann sums. So let's go ahead and put our rectangles in here. They want us to use left-hand Riemann sums. So what is that going to look like then? Well, if I look at these two and I use a left-hand Riemann sum, I'm going to use this as my rectangle. So I take my height is the 0 height, it's on the left-hand side, right? It's the left-hand side. So my height at 0, we said, was 1340. So I've got my height, 1340, times the width, which is 1, right? Everybody okay so far? Plus my height here, that's the height at 1, right? We said the height at 1 was 1190, so that's going to be 1190, times the width of this is 2, plus the height here, right? We said the left-hand side, so the height at 3 is 950, I believe. Yep, 950, times the width of this rectangle, which turns out to be 3 because we're using left-hand sums. Plus, finally, over here, we get the height at 6, and we said that was 740, times the width of that, which is 2. And if we do our arithmetic, we end up with there 8,050 liters as our estimate for the amount of water that's being removed from the tank in the first 8 hours. Now it also says at the bottom, it asks a second question. Is this an overestimate or an underestimate? Well, if we draw our Riemann sums, our rectangles, pardon me, if we draw our rectangles, right, we can see that we have overestimated. So what do we need to say? We need to say this is an overestimate because the function is decreasing. Because it says specifically, is this an overestimate or an underestimate? Give a reason for your answer, right? So it's an overestimate because the function is decreasing and we use left-hand intervals, we ended up overestimating. So that's the answer to part B. Now part C, another typical problem in here, part C says, use your answer from part B to find an estimate for the total amount of water in the tank to the nearest liter at the end of the 8 hours. Now, what do we have to think about with our tank? Right? I'm just going to draw a cylinder as my tank. So here's my tank. Remember, when time began, in the tank, we had 50,000 liters, right? That's what they told us. We had 50,000 liters. Now, what's been happening in these 8 hours? Well, we know for a fact in those 8 hours, we've taken 8,050, that's our estimate, 8,050 liters of water out of the tank. So I'll write that as a negative. But water has also gone into the tank, right? We've also put water into the tank. There has been water going into the tank for the 8 hours, given to us by this function right here. But that's not the amount of water in the tank. That's the rate of the water going into the tank. So I need to turn that rate into an amount, just like I did in part B. So the amount of water that's gone into the tank is going to be the integral from 0 to 8 of WT dt. And since this is a calculator problem, they expect us to use our calculator to find that. So what do we know for part C? We know for part C, we'll just switch to red here. We know the total water in the tank after 8 hours. That's what they asked us to find. It's going to be the combination of these three things. So it's going to equal the 50,000 gallons we started with minus the estimate for the 8,050 gallons that we've removed, that we found here, plus the amount of water that's gone in. And since that's a rate, I have to integrate that to get an amount. This is, again, the net change theorem. It's very common on the AB test and the BC test in the past. So this is going to be the integral from 0 to 8 of WT dt. And I would use my calculator to find that because we can't integrate that without a calculator. And if you do that arithmetic correctly, you should end up with about 49,786 liters as the amount of water in the tank at the end of 8 hours. Okay, so again, net change theorem here, we had a rate, I needed an amount, so I took the integral. Net change theorem here, I have a rate, I need the amount, so I took the integral. Very common questions on the AP test for the rate. Can you remember the net change theorem and turn it into an amount? Part D says, for 0 to 8, between that time, is there a time when the rate at which the water is pumped into the tank is the same as the rate at which the water is removed to the tank? I.e., what they're asking in part D, is there a time t, 0 is less or equal to t is less or equal to 8, when W of t equals R of t. Right? That's what they're asking us in part D. Is there a time when this happens? Now, they don't expect us to solve this because we can't put this equation, right, W of t, and R of t into our calculator and push the solve button. We don't have R of t. So there must be a way to answer this without doing the actual algebra, right? That's what we have to figure out. And how are we going to do that? Well, what do we know about these functions? Well, we know this function is continuous. We can look at this function. We can see it's an exponential times 2,000. That's continuous. We know this function is continuous because they told us it's differentiable. Since they told me it's differentiable, it's continuous. I have two continuous functions. Now, what do I know, right? What do I know about these two continuous functions? Well, this is where we have to maybe stretch ourselves a little bit. We have to think, okay, I have two continuous functions. I want to know if they're equal. What does that mean? If they're equal, that means their difference would be 0, right? That means WT minus R of t would equal 0. That's really the question they're asking us. Is that possible? Is it the case that they equal 0? So since they're continuous, right? Since they're continuous, is there a time when this is going to be 0? Well, this is an intermediate value theorem question. It's what they're hoping you can pull from this. They're hoping you can think this through, take these pieces that they've given you, these hints, and come to the conclusion, wait a minute, I want to know if it's going to be 0. Well, if it's bigger than 0 at some time and smaller than 0 at another time, then I'm going to know it has to equal 0 for some time in between because it's continuous, right? Here we said if the difference is bigger and smaller and it's continuous, then there's going to be some time where it's going to equal 0. So that's the intermediate value theorem. Well, what do we know about Wt minus R of t? Well, we know that at time 0, right? What do we know about what's going on at time 0? Well, at time 0, we know, right? We know the rate that water is going in. We can find W of 0. If we put a 0 in here, we get 0 divided by 20, that's 0. E to the 0 is 1. We get 2,000 for this, right? This is 2,000. We know what R of 0 is. If we take a look at our chart, they give us R of 0. R of 0 is 1,340 liters. It's up in the chart. We haven't used it anywhere. Well, actually, we used it right here, I guess, so that we hopefully remember that. So what does that mean? 2,000. This is greater than 0. So this function, the difference between these two functions is positive at time 0. What's going on at time 8? Well, we found, right? We can find out what's happening at time 8. How are we going to find out what's happening at time 8? Well, we're going to plug 8 into here with our calculator, and we're going to get a number. And we know what's going on at time 8 we know this is 700. Okay? Now, I'm not going to do the arithmetic. I'm not going to do that math. But if you plug this in to this, you get a number smaller than 700. Okay? Now, I don't know what that number is. But this number that you get right here is less than 700. So when I take a number less than 700 minus 700, I get negative. And I get this picture right here. So what do we say to answer part D? We say, well, this function is continuous. We have to explain that. Why is it continuous? That function is continuous because of the nature of the function. This function is differentiable, so therefore it's continuous. And we know the difference of two continuous functions is continuous. It goes all the way back to chapter 2, having conversations about continuity. It actually goes back to pre-calc, having conversations about continuity. Then we find out that that function is positive at 0. The function is negative at time 8. So since it's gone from above the x-axis, the t-axis, to below the t-axis, it had to cross the t-axis. Therefore, yes, there is a place. I don't know what it is. I can't find it, but I know there's a place where there's a value of t where the rate at which the water is going into the tank is equal to the rate at which the water is going out of the tank. Okay? Now that completes problem 1 of the 2016 AB and, as it turns out, BC free response exam. So I'm going to skip to question 3 right now, only because that's also on the BC exam. So I'm going to skip to question 3. That way the BC students can watch question 1, which we just finished. You can watch question 3, which I'm about to do, and then you can exit this video and go pick up your question 2 on the 2016 BC video, which will have your question 2 on it. And then I'll do, at the end of this video, if you're an AB student, don't leave it at the end of this question, and I'll go ahead and do your question 2 right after this question 3. So we're going to do question 3 just because it's on both tests, all right? Question 3, I love these questions. I'm very, I don't know, I just like solving these kind of problems. And they put these on the AP test often. They're not a constant guaranteed problem every year, but they're on the test quite often. And so they give us a diagram, and it says the figure above shows the graph of a piecewise linear function f defined between -4 and 12. All right. So I'm going to draw a quick sketch of this function because we're going to need it. And we're defined between -4 and 12. Okay? So what do they give us? They give us -4, -2, and so this would be 2, 4, 6, 8, 10, 12. Okay? And so we have -4, -2, 2, 4, 6, 8, 10, and 12. So we have a function, and we have a graph of the function. So at 0, this is equal to 4. All right, so we'll make 4 right here. It's -4 here. So our first piece of our function looks like this. Okay, so this is -4, sorry, and this is 4. Now at 2, we're 0, and at 4, we're 4 again. So we're here. At 2, we're 0. At 4, we're 4 again. All right? Now at 6, we're 0, and at 8, we're -4 again. All right, so we have this. And then at 10, we're 0, and at 12, we're -4 again. All right. So this is our graph that they've given us, and this is, remember, the graph of f. Right? This is f. And they've told us this is a piecewise linear function. Now, they've defined for us a new function, g. And g is our friend, the area accumulating function from 2, make sure you see that, from 2 to x of f of t dt. So what is g? G is the integral from 2 to x. So it starts here, and if I'm going this way, it's the area under these curves. It's the area under this triangle, the area of this triangle, the area of this triangle. If I go this direction, now my bounds would be reversed, right? We're going to be careful about that because it would be from 2 to -2. My bounds would be backwards. So I'm going to have to be careful when I do this because they didn't start us at -4. They didn't start us over here. They started us at 2. So we want to be careful for that. All right. It says in part A, does G have a relative max, a relative min, or neither at x equals 10? Justify your answer. All right. So how are we going to do that? Does it have a relative max or a relative min at x equals 10? So that's part A. G of x, relative max, min, or neither at x equals 10. So what do they want me to do? They want me to play my max-min game, and I know how to do that. You know how to do that. We take the derivative, we set it equal to 0 to find our critical values, and then we either set it equal to 0 or see where it fails to exist, and then we check our first derivative test. That's what we're going to do here. We're going to conduct a first derivative test. But it's not a traditional first derivative test. They didn't give me a function that's a traditional take the derivative set it equal to 0. They gave me this kind of a function. Now what do I have to do? I've got to find g prime of x. Now we know how to do that. We know g prime of x is the derivative of this function. That's the fundamental theorem of calculus part 1. We know that's f of x. All right, we know how to take the derivative of that. It's f of x. If you don't remember that, go back and review the fundamental theorem of calculus part 1. So, if we're going to have a relative min, relative max at x equals 10, x equals 10 has to be a critical value. In other words, g prime of 10, which is f of 10, right, g prime equals f, must equal 0 or fail to exist, right? Well, if I look at f, this is the graph of f of 10 is 0. F of 10 equals 0 means x equals 10 is a critical number. All right, so now we're going to do the sign test. Now, how are we going to do the sign test? Well, we're going to put 10 here because that's 10. 10 is the only critical number we want to know about. And we have to figure out what's g prime, right? If g prime goes from positive to negative, increasing to decreasing, this would be a max. If it goes from negative to positive, decreasing to increasing, this would be a min. If it doesn't change sign, it's neither. Well, we don't know g prime of x. We're going to plug in test points, but we do know g prime of x is equal to f of x. So that's how we're going to do, that's how we're going to do this. We're going to come over here and we're going to go, well, pick a number smaller than 10, right? Pick a number over here as my test point. What do I know my functional value is? Well, it's below the x-axis, so I know my functional value is negative then, right? So f is negative, which means g prime is negative, so the function's going down. What about on this side? Well, on this side, I'm also negative. For my other test point, I'm also negative, so I get negative to negative, so x equals 10 is not a local min nor max because g prime does not change sign. At x equals 10. So they're making us run our sign test. They're making us find our local min, local max, show them that we can do that analysis, but they're not giving us a traditional, hey, find the derivative of this function kind of question. Okay? Very common on the AP test. Part B, does the graph of g have a point of inflection at x equals 4? So here we go. They're going to continue this journey for us, and they're going to ask us about inflection points. Is x equal 4 an inflection point? Now, how do we do that? Well, we know how to find an inflection point. We look at the second derivative, right? So, does g have an inflection point? So I need the second derivative of g. So I have to find g double prime. Now, how am I going to do that? Well, I know what g prime is. G prime is f of x. So I take the derivative of this side, g double prime. I take the derivative of this side. G double prime is f prime of x. It's the slope of this. Now they want to know, what do we get at x equals 4, right? So the first thing we have to ask ourselves, right, is this a critical number of the second? Is x equals 4 going to be 0? Does g double prime of 4 equal 0 or fail to exist? Because if it doesn't equal 0 or fail to exist, it's not a critical number. And if it's not a critical number, it can't be an inflection point. Now, if that didn't make any sense, listen to it like 4 times. Just back the video up and listen to it again. What do we know g double prime of 4 is? right? What do we know about G double prime of 4? G double prime of 4, right? G double prime of 4 is the slope of f, right? G double prime of 4 is the slope of f at 4, i.e. f, not double prime, f prime of 4 equals question mark. Well, that's the slope of this graph at 4. That's a corner, so we know f prime of 4 fails to exist. Well, there we go. F prime of 4 is G double prime of 4. It fails to exist, so that's a critical number. So now I can run my sign test. So here's 4. I'm looking at G double prime, which is F prime, right? So what's the derivative of F on this side of 4? I need a test point. Well, the derivative of f is the slope of this tangent line, that's plus. On this side of 4, the derivative of f is the slope of this tangent line, that's minus. It changes sign, so therefore G has an inflection point at x equals 4 since f prime changes sign at x equals 4. So once again, they've asked us about something that we're quite capable of doing. If you give me a function, I take the derivative, I set it equal to 0, I see where it fails to exist. I talk about mins and maxes. I take the second derivative. I set it equal to 0, I see where it fails to exist. I talk about inflection points. But they love to take us out of our comfort zone. And this type of problem is very typical of the type of question where they ask us about mins and maxes. The traditional mins and maxes questions are always in the multiple choice. Now, on the 2020 test, we don't have multiple choice. So if they're going to ask us about mins and maxes, this is probably the way they're going to do it. All right, what about Part C? Right? What does Part C ask? Part C says, find the absolute max and the absolute minimum of G for 0 to 4. Justify your answers. All right, they want us to find the absolute min and the absolute max. So how do I find the absolute min and the absolute max? First, to find the absolute min and the absolute max, I have to find the critical numbers. I test the critical numbers and the endpoints. To find an absolute min and an absolute max, we use the closed interval method from chapter 4. And the closed interval method said, you've got to test the endpoints and test all critical numbers. All critical numbers. And whichever of those is the biggest y value, that's going to be your absolute max. Whichever of those is the smallest y value, that's going to be your absolute min. So, where do we go to find critical numbers of G? We've already written that down, right? We said we want to know where G prime equals 0 or fails to exist. We know G prime, right? G prime equals 0 wherever G prime is equal to f of x. So when does f of x equal 0, right? Now, for it to be a relative min or relative max, it has to equal 0 and it has to change signs, right? Like, for example, we can eliminate 10. It equals 0 over here at 10. We can see that, right? Where does it equal 0? It equals 0 here, it equals 0 here, it equals 0 here, and it equals 0 there. So those are our potential locations, right? Those are our critical numbers. But we can eliminate 10 from the list. We don't have to find g of 10 to know whether that's a min or a max. We've already said g of 10 is not a relative min or a relative max. We've eliminated that one. This is a no. And the reason it was a no is because the derivative was negative on this side and negative on this side. The graph was below, and the graph turned out to be the derivative. The graph turned out to be the derivative. Well, take a look over here. The derivative is the graph. It's positive there, and it's positive there. So this, by the same reason that that's a no, this is also a no. So in part C, where they ask us where are the relative mins, where's the absolute min and the absolute max? Let's just make some room right here. We want the absolute min and the absolute max. We only have this value and this value as our critical numbers. So we know our possible values, right, x, are going to be the endpoints. So we have -4, we have 2, we have 6, and we have 12. Now what do we do over there? We have to find g of x for each of these, right? Now how are we going to do that? Well, we're going to use this, right? So this is going to be the integral from 2 to -4 of f of t dt. This is going to be the integral from 2 to 2 of f of t dt. This is going to be the integral from 2 to 6 of f of t dt. And finally, this is going to be the integral from, 2 to 12 of f of t dt. Now we can evaluate each one of those. What's the integral from 2 to -4? Well, the integral from 2 to -4 is the area under here, isn't it? But it's not really the area under there, because these bounds are backwards. We're going to have to put a negative sign in front of that. So what do we get? Well, the area here, this is base is 4, the height is 4. So the area of that is 8, right? Well, we'll just go ahead and write these in. The area of this is 8, the area of this is 8, the area of this is 8, the area of this is going to be 4, and this likewise is going to be 4. So what are we going to have? Well, if we integrate from 2 to -4, that's the same as integrating from 4 to -2 with a minus sign out in front. So if we integrated from 4 to +2, pardon me, -4 to +2, there I said it right that time, we would get +8, take away 4, take away because it's below the x-axis. 8, take away 4 would be 4, and so we get a negative because we reversed the bounds. What's the integral from 2 to 2 going to be? Well, that's going to be 0. How about the integral from 2 to 6? Well, the integral from 2 to 6 is the area of this. That's going to be 8. And how about the integral from 2 to 12? Well, the integral from 2 to 12 is going to be 8, right? Starting here, going to here. It's going to be 8, +8. Take away 8. That's 0. Take away 4. That's going to be -4. And so the question says, right, find the absolute minimum and the absolute maximum of g. And so justify your answers. Well, our absolute minimum, right? Our absolute minimum. Oh, I put the wrong number here, didn't I? This is supposed to be -2, isn't it? I am so sorry about that. Let me go back and fix that. So that's 2 was a no, wasn't it? I'm so sorry. So -2 goes there. So this is the integral from 2 to -2, isn't it? From 2 to -2. So what's the integral from 2 to -2? Well, we're going backwards, right? We're going backwards. So we're going to have to put a minus sign here. It's the area of that, so it's -8. So this is our absolute min, isn't it? Yeah, there it is. and this is our absolute max. So our absolute minimum is -8, right? Is -8, and it occurs at -2. Our absolute max is 8, and it occurs at +6. Okay, +6. So that takes care of part C. Let's just go ahead and get this out of the way. Let's go ahead and work out part D. So what does part D say? For x between -4 and 12, find all the intervals for which g of x is negative. When is g of x negative? Now, we know g of x is this integral, right? This integral. When is this going to be negative? When is this integral going to be negative? So we're going to look, that's our area, right? We're going to look here and ask ourselves, when is g of x going to be negative? Now, if we just start from 2 and go to 12, right? If we start from 2 and go to 12, what do we know? Well, from 2 to 6 we're positive, right? So remember, this has to start at 2 for g, right? We want to know, when is g going to be negative? So we have to start at 2. So if we go from 2 to 6, we get +8, right? We get +8. What happens if we go from 2 to 10, right? 2 to 10. Well, we're trying to find the x value, so maybe I'll explain it like this. We start at 2. What happens if I pick this x? Well, I get this rectangle, this triangle, positive. If I pick this, I get this rectangle, positive. What happens if I pick this? I get, 2 to 5. Still positive. I would have all of this. If I get to 6, I've got all of this. Now, when I move over to here, right, say I pick 7, I'm still going to be positive. G of 7 is positive because it's the area from 2 to 7. So it's this little negative piece, but that huge positive piece. What happens if I go to 8? Well, it's this negative piece along with that big positive piece, so I'm still positive. What happens at 9? Well, I've added some more negative, but not enough to offset the +8 here. I don't get back to 0 until I get to 10. But what happens when I pick 11? Well, when I pick 11, I get this negative piece, this positive. These two triangles offset. That's negative, so I'm going to be negative at 11. I'm going to be negative at 10.5. I'm going to be negative at 11.5. So one interval where we're going to be negative is 10 is less than or equal to x is less than or equal to 12. Because I start here, I go all the way here to get back to 0. I'm positive, positive, positive 8. Then I finally get rid of the 8, and then I get back to negative after I cross 10. What about going the other way? Well, going the other way is kind of backwards, right? They're making us think this through here. So they're making us reverse this, aren't they? So when I do 0, right, what does g of 0 look like? It looks like the integral from 2 to 0 of f of t dt. But that's minus the integral from 0 to 2 of f of t dt, isn't it? Because the bounds are backwards. So I have this integral right here, this triangle, which is +4, but I have a minus here, so that's negative. When I go from 2 to -2, right, what's g of -2? G of -2 is the integral from 2 to -2 of f of t dt. We just figured that out in the last one. We found that to be -8. That was our absolute minimum. So this is negative. Now what happens when we get over here and start plugging in these numbers, like g of -3? Well, what's going on at g of -3? We have this, which is all negative because we're going backwards. This is all -8. And over here we only have this little piece of the rectangle, triangle, which is negative, but because this negative becomes positive. But that positive is not big enough to offset this -8, so this is still going to be negative. In fact, it's going to be negative all the way between -4 and 2. All right? So that's the answer to part 3. Part D. All right, so at this point, the BC students, you can leave this video, go look at the 2016 BC Calc number 2 video, which would be your answer for question 2. And AB students, don't leave, because we're about to do your question 2 right now. All right, so BC students, nice to see you. Thank you for watching. All right. So here we go with AB question 2, right? AB question 2. So this question is about velocity and acceleration and distance, okay? So it says for t greater than 0, a particle moves along the x-axis. So we have an x-axis, and our particle is moving back and forth along this axis. The velocity of the particle at time t is given by this function. So we have a function for velocity. Now this is a calculator question, so don't panic over this function. V of t is 1 plus 2 sine, 1 plus 2 sine t squared over 2. All right, so that's the velocity of our function. And they tell us that at time equals 4, right, here's 0. We're going to call this 2. Our particle is right here when t equals 4. That's all we know, right? At t equals 4, at t equals 4, our position is 2. So S of 4, our position is 2. Okay? Now, it says, at time t equals 4, is a particle speeding up or slowing down, right? Speeding up or slowing down. So what do we need to know? Well, we need to know its velocity at time t equals 4. So how are we going to find that? Well, if we find its velocity at t equals 4, that would be v of 4, right? Now we would use our calculator for this. It'd be 1 plus 2 sine, right? We would plug a 4 into here, and we would get 16 over 2. And if we plug that into our calculator, we get 2.978716. 2.978716. Now the important thing is that's positive. All right, it's positive. So what does that mean? It means our particle is moving this direction at time t equals 4. Now that doesn't tell me if it's speeding up or slowing down. It just tells me it's moving to the right. To know if it's speeding up or slowing down, I need to know what its acceleration is. I need to know a of 4, which of course is v prime of 4. And if I take the derivative of this, right, if I take the derivative of this, I would get 2. The derivative of sine is cosine. I get t squared over 2. Then I have to do the chain rule. I've got to take the derivative of what's inside, and I get 2t over 2. And so our derivative is 2 cosine t squared over 2, and then all of that gets multiplied by t. And now we plug in a 4, and when we plug in a 4, we get negative 1.164, which is less than 0. Now what does that mean? Well, in terms of what that means about our particle, is it means its velocity is going to the right. That's its velocity. but its acceleration is going to the left. And if you're moving to the right, but your acceleration is going this way, that means you're slowing down. Your acceleration is not pushing you faster and faster and faster. Your acceleration is actually pushing against you. So you would say the particle is slowing down. The particle is slowing down since velocity and acceleration have different signs. Okay, so the particle is slowing down because they have different signs. So that's part A. Right? That's part A of number 2. What about part B? Find all times t between 0 and 3 when the particle changes directions. Justify your answer. All right, so when does it change directions? So that's going to happen when the velocity changes sign. If the velocity is positive, we're moving this way. If the velocity is negative, we're moving this way. So what do we want to know? We want to solve v of t equals 0, right? And how would we do that? We use our calculator. And we ask our calculator to solve 1 plus 2 sine. In our calculator, we would write it as x squared over 2, of course, equals 0. Now, you may want to watch a quick video on how to solve things on intervals, because if you ask your calculator to solve this, it's going to give you an infinite number of solutions, because we all know sine equals 0 a bunch of times. So this is going to give you a bunch of answers. You want to tell your calculator, only look for the answers between 0 and 3, and there are many videos on the internet that show you how to do that, and that's a skill I would want to take into the AP test with me. Now, when do we get it equal to 0, right? Because in order for us to change directions, we've got to stop. So we've got to look to see, does the velocity ever equal 0? Does that ever happen? And when we solve this, we get t equals 2.7074. So we get t equals 2.707468. So there is a point between 0 and 3 when I stop. Now, that doesn't mean I change directions, right? That doesn't mean I change directions. It just means I stopped. It just means I've stopped. I know I've stopped right here. But what could I have been doing? My particle could have been moving like this. It could stop. And then it could keep moving like this. I haven't changed directions. So what do I need to do? I have t equals 2.707468. I need to plug in a time after that and a time before that. You need to take a time bigger than this and a time smaller than this, right? So maybe this one is t equals 2.707. We'll just start there. And this one over here is going to be t equals 2.707, and instead of a 4, we'll put a 5. And then you're going to find v of t here using your calculator. You're going to find v of t here using your calculator. All right. And what are we going to see? We're going to see that this one's positive when we plug it in. I'm not doing the arithmetic for you on the video. We're going to see this one is negative. So what does that mean? It means our particle was moving to the right. Velocity was positive here. But over here, velocity is negative, so now our particle's moving to left. So indeed, our particle has changed directions, and we would want to write that out. We need to explain this to the reader. It says in part B, justify your answer. So you would have to explain that. You would say, well, I had to find when the velocity is 0. I did that. And then I had to check to see if the velocity changed sign. So I plugged this number in and I plugged this number in. I got positive to negative. So yes, it changed signs. Part C says, Find the position of the particle when t is 0. All right. Where is our particle when t is 0? Now, that's position. And we know s is the integral of velocity, right? That's what we said in class. We said the derivative of s is velocity, so therefore the integral of velocity undoes that. That's s. But what will that tell us? Well, this will tell me how far I've moved. So if I integrate this, right, if I integrate this between 0 and 4, what is that going to tell me? That's going to tell me how far I moved. But that's not the answer to the question. They want to know, where are we at time 0? What's our position at time 0? Well, this tells me how far I moved. So if I know I've moved 3, right? If I've moved 3, look right here. Look right here. At time 4, I'm sitting at 2. But this told me I moved 3. So if I moved 3 to get to position 2, where did I start? Right? Where did I start? Well, I started at 1, negative. I had to start here at -1 because I moved 3, and the problem told me at time 4, you're sitting at 2. So 4 seconds into this, you're sitting at 2. But during those 4 seconds, I know you moved 3. So since you moved 3 and you're sitting at 2, you had to start at -1. So we have to take into account where we began to figure out where we end up. So position this, right? This is distance moved. And it's not really distance, it's displacement. Right? That's what that is. I need to know that, right? How different am I from where I started? Now, when we do that integral, right? When we do that integral, which we can do on our calculator, we can do that integral. We get this. We get -5.815027. All right. So that tells me that I'm this far, right? This far away from where I started. So where did I start? Well, I started, if I add 2 to this, because they told me 2 here, I can see where I started. So I started at -3.81527. Right, that's where I started. All right, what about part D? Part D says find the total distance traveled. Now, we just said that's displacement, and during class, we had a big conversation about the fact that distance, right? Distance is the integral of the absolute value of velocity. That's distance. And so what do they want me to do here? Oh, I'm sorry, it says times 0 to 3, doesn't it? 0 to 3. So they want me to find the distance I traveled between 0 and 3. So we would do this on our calculator. We would ask our calculator to integrate. We would choose the absolute value command, and we would put the absolute value in front of this, and we would integrate between 0 and 3. So it's just a mechanical, can you do your calculator, can you use your calculator, and you end up with 5.301. Now, if you don't know where to find absolute value on your calculator, right? Because if we were doing this problem, what would we have to type into our calculator? Here, before I exit the video, I'll show you what you would have to type into your calculator. right? In calculator symbols, what would we have to type in there? Well, now somewhere at the beginning of this problem, since it's a calculator problem, I would have defined, right? I would have said define y of x equal 1 plus sine, right? And I would have said x caret 2 divided by 20, right? Because that was the function, oh, sorry, divided by 2. That was the function they gave us. So I would have typed that in already, and I guess I wrote it wrong. So it's 1 plus 2 times, right, sine. And of course, we don't use t on our calculator, so we would be using x. Now, how would I do the integral, right? How would I do the integral from 0 to 3? And I would need it to be the absolute value of d of t dt. Now, that, in my calculator, I would choose my integral command, right? F3 integral. Then you have to hit catalog. Catalog. Because there's no absolute value key. You've got to hit catalog, and the very first thing that comes up is ABS, absolute value. So you would have this in your window, then you would hit catalog, you would highlight this, and it would say ABS open paren. Then you would type in there y of x. Okay? So we would have integral absolute value y of x, comma x, right? Tell it I'm integrating with respect to x, comma 0, comma 3, lower bound, upper bound, and then when you do that, you should get 5.301. All right, so that's the end of the 2016 video for questions 1, 2, and 3. All right, keep studying, keep working.